Hi, welcome back to the course. This is still mechanics and we're now on lesson 9. And lesson 9 is about your fluid mechanics. This will be our goals for this lesson. First, we're going to study the concept of density and we're going to investigate pressure in a fluid. And after that, we're going to study buoyancy in fluids. Then we're going to compare laminar versus turbulent fluid flow and how the fluid speed depends on the size of the tube. And lastly, we're going to learn how to use Bernoulli's equation to relate pressure and flow speed of a fluid. Fluid mechanics is divided into two sections. So we have your fluid statics and then your fluid dynamics. On the first videos, you're going to discuss first your fluid statics, and then after that, we are going to move forward to your fluid dynamics. Just some quick question before we start the lesson proper. I believe you've already seen sharks and fishes even in some videos. And the question is, why must the shark keep moving to stay afloat while the small fish can remain at the same level with little effort? So if you have observed, sharks tend to keep moving in order to stay floating on the ocean. While if you observe fishes, they just stay stationary, but they still float. So in this lesson, we're going to answer this, or we're going to answer questions like this. We begin with fluids at first, which is your fluid statics, and then move on to the more complex field of fluid dynamics. As I've said in the beginning part of this video, your fluid mechanics is divided into two sections. You have your fluid statics and your fluid dynamics. Your fluid statics, this is the study of fluids at rest in equilibrium situation. And your fluid statics is based on Newton's first and third laws. Your fluid dynamics, on the other hand, is the study of fluids in motion. And this is much more complex. And this is believed to be the most complex branch of mechanics. Let's first talk about your density. The density of a material is its mass per unit volume. So your density is given by rho is equal to your mass over your volume. Its SI unit is in kilograms per m cube. And what do you think is the densest material found on Earth? The answer to this one is your metal osmium with a density of 22,500 kilograms per cubic meter. The specific gravity of material is its density compared to that of water at 4 degrees Celsius. So if you want to compare something with your water, which is the density of 1,000 kilograms per m cube, you can also use your specific gravity. If you're going to work, say for example, in chemical industries or in industries which have their chemical analysis section, you would observe that at most times the chemicals will be analyzed using their specific gravity in order to say that the chemicals that will be used into the production is the right chemical that is used in making the product. So we have here different mass but the same density. So you have a steel wrench and then a steel nail. They may have different shapes and different masses, but they are made of the same steel, so they have the same density. Because the wrench and nail are both made of steel, they have the same density, that is their mass per unit volume. These are some of the densities of some common substances, and it will be good to take note of the following materials, the density of the following materials. You have the density of air, that is at 1 atmospheric pressure at 20 degrees Celsius. The density of air is at 1.20 kilograms per m cube. Ice, on the other hand, has a density of 0.92 times 10 to the third kilogram per m cube. Your water has a density of 1,000 kilograms per m cube. While you compare it with your seawater is denser with a density of 1,030 kilograms per m cube. So this is actually the reason why we float more on seawater than on ordinary water, because of the density of these substances. Um, Gold, on the other hand, has a density of 19.3 times 10 to the third uh, kilograms per cubic meter. And if you're going to compare this one with the density of a neutron star, the density of a neutron star is around 10 to the 18th kilogram per m cube. So why do we measure the density of a material? So the density of a material has many um, uses. Like say for example, it can be used to determine the charge condition of a storage battery by measuring the density of its electrolytes. So there is this known value, the density of the electrolytes, and you can compare this one with the density of the electrolytes in your materials, and then you can say that uh, this battery is still a good charge condition, or this battery needs to be replaced. In automotive, permanent type antifreeze, which is a solution of ethylene glycol and water, uh, has a freezing point of a solution which depends on the glycol concentration. And you can get this glycol concentration by taking note of the density of your antifreeze material. Your antifreeze material is usually used in areas which have very cold temperatures. Let's have a quick example, which is the weight of a room full of air. So find the mass and weight of the air at 20 degrees Celsius in a living room with a 4-meter by 5-meter floor and a ceiling of 3-meter high, and the mass and weight of an equal volume of water. So again, find the mass and weight of the air at 20 degrees Celsius in a living room with 4 by 5-meter floor and ceiling of 3 meters high, and the mass and weight of an equal volume of water. So in the problem, you have a room. In this room, you're going to fill this one with air, and on the next scenario, you're going to fill the room with water, and you're asked to find for the mass and weight of the air that can fill this room and the mass and weight of water that can fill the room. So just from your density, again, your density is just your mass over your volume. So we can get the mass of air, which is equal to the density of air times the volume of the room. Here, you have the density of air, which is at 1.20 kilograms per m cube. And you have here the volume of the room. So you have 4 times 5, which is 20, times 3, which is 60 m cube. So your m cube cancels out. So you have 120 kilograms per m cube times 60 m cube. And you have the mass of air that can fill the room, which is equal to 72 kilograms. The weight of air is just your mass of air times your acceleration due to gravity. So we have 72 kilograms times 9.8 meters per second squared, which is equal to 700 newtons or 160 pounds. The mass of water, on the other hand, that can fill the room is equal to the density of water times the volume of the room, which is equal to 1000 kilograms per m cube times 60 m cube, which is equal to 6 times 10 to the 4 kilograms. The weight of water, on the other hand, is just your mass of water times the acceleration due to gravity, which is equal to 5.9 times 10 to the 5 newtons, or this is equal to 1.3 times 10 to the 5 pounds, or this is equal to 66 pounds. So as you can see, there's a big difference when you're going to fill the room with air and filling the room with water. And it all varies because of the density of these fluids. And by the way, when we are referring to fluid, when we are going to talk about fluid, this does not only mean about your liquid, but fluid is anything that flows, so your air can flow. So gases and liquids are your typical fluids. Now let's talk about the pressure in a fluid. So when a fluid is at rest, it exerts a force perpendicular to any surface in contact with it. Example, you have a body immersed in a fluid. Now, consider the figure here on the right. So we have here a body, a small surface area with area dA, and infinitesimal area dA within a fluid at rest. Like say, for example, the fluid in a swimming pool or the fluid inside a glass of water. Now, if you're going to immerse this body here of area dA in a fluid that is at rest, which is this fluid here surrounding the body, this fluid exerts a force to any surface in contact with it. So, since this fluid is in contact with this body here, the fluid exerts a force which is perpendicular to any surface of the body. So this surface area here has at least two areas in which the water can make in contact with. So you have this area here, and the fluid exerts a perpendicular force to this area dA. Another segment of this area is at the back of this one, at this point here. So the fluid in this area also exerts a force on this side of your surface area. Now, this is the force that you feel pressing in your legs when you dangle in a swimming pool. So if you try to imagine and you're sitting in the pool side and then you dangle your legs on the swimming pool, you'll feel some force exerted on the water on you. And that force is what you call your pressure, which is always perpendicular to the surface in which the fluid is in contact. So here, the surface does not accelerate, so the surrounding fluid exerts equal normal forces on both sides of it. The fluid cannot exert any force parallel to the surface, since that would cause the surface to accelerate. So if you try to see if the fluid exerts force parallel to the surface, either here or here, your surface area here might accelerate upward or downward. Now, this pressure is the same pressure that you'll feel when you try to wave your hand like this. You feel something in this side here and also on this side here. So that force that you feel is the force exerted by the fluid in this room, which is, say, the air inside this room. So that pressure is perpendicular to the surface and also perpendicular to the surface. So the pressure in a fluid is the normal force per unit area. That is, mathematically, the pressure for this surface area here is equal to your dF perpendicular over dA. Or your pressure is just your force per unit area. So you have your pressure is equal to F over A. So again, the pressure in a fluid is the normal force per unit area. That is, your pressure is equal to dF over dA. If the pressure is the same at all points, say for example anywhere around here you have the same pressure that is applied by the fluid, your pressure is just equal to your F perpendicular over your area. The SI unit of your pressure is in Pascal. So you have your 1 Pascal is equal to 1 PA, that is equal to 1 Newton per meter squared. In the figure, the surfaces differ in area and orientation. The first figure here is oriented like this case here, and the other one is oriented like this. But the pressure on them, the force magnitude divided by the area, is the same. So here you have a pressure on this side, which is equal to dF perpendicular, and you have a unit area of dA. So this is just your dF over dA. Here you have a force exerted by the fluid, which is equal to 2dF perpendicular, but your surface area is twice as large or twice as big as your first figure. So in the situation here, both the surfaces experience the same pressure even though the surface are different in their area and orientation. So we have this what you call your atmospheric pressure, and you always hear this one, your atmospheric pressure, PA. The pressure on the Earth's atmosphere, which is the pressure at the bottom of the sea of air in which we live in, is equal to your PA. In average, this is equal to 1 atm or 1 atmospheric pressure. And your 1 atmospheric pressure is equal to 1.013 times 10 to the 5 pascals. Or in other units, you have 1.013 bar or 1013 millibar, or this is equal to 14.70 pounds per inch squared. To be exact, 1 atm or 1 atmospheric pressure is equal to 101,325 pascals. Example, in the room described in example 1, what is the total downward force on the floor due to an air pressure of 1 atm? So the area of the floor is equal to 20 meters squared. And you're asked for the force exerted on the floor due to the air pressure of a pressure of 1 atm. So your pressure is just your force per unit area. That means your force is equal to your pressure times your area. The pressure of the air at 1 atm is equal to 1.013 times 10 to the 5 Newton per m squared, or this is equal to the pascals times 20 meters squared. So that means the force is equal to 2 times 10 to the 6 Newton, or this is equal to 4.6 times 10 to the 5 pounds, or you have 230 tons. Now, if the weight of the fluid can be neglected, the air or the pressure in a fluid is the same throughout the volume. But fluid's weight is not negligible. For example, the atmospheric pressure is less at high altitude than at sea level, which is why an airplane cabin has to be pressurized when flying at 35,000 feet. Pressure increases rapidly with increasing depth below water surface. That is why when you're going to swim deeper and deeper into the ocean, or even just in a swimming pool, you feel this force that is hurting your eardrums, okay, or your ears. And that force that you feel tends to become stronger as you go down deeper, because of the fact that your pressure increases rapidly with increasing depth below your water surface. So there is a change in air pressure as you go downwards to the ocean floor, or as you go upwards at higher altitudes. And that is because the weight of the fluid cannot be neglected. By the way, some clarifications. When we're going to talk about fluids, we do not only mean your liquids, but the fluid is anything that flows. So like say for example, your gases, they also flow in your environment. So here when you're talking about fluids, we're referring to both your liquids and then your gases. Now consider this glass here. It's some fluid element, and you have an element of fluid that is at rest with an area A and thickness dy. And let us assume that the density rho has the same value throughout the fluid as does the acceleration due to gravity. So what we mean here is that assume that anywhere around this container here, this fluid here, let's say that the density doesn't change, and also the acceleration due to gravity. So we take some small element here of fluid at rest with an area A and thickness dy. So an infinitesimal thickness dy and area A at some height y with respect to our reference, which is at the bottom surface of the glass, which is our y equals 0. So again here we have your fluid element at rest with an area A and thickness dy. And Let us take the forces exerted on this fluid element here by your fluid, and then all other external forces. So again, our reference point is at the bottom of the glass, which is your y equals 0. And at this area here, at the bottom area of your fluid element, the pressure exerted here, which is the force due to pressure at the bottom surface, is equal to your P times your A. On the top surface here, since you are changing from some height dy, so at the top surface, your pressure is equal to your P plus dp on the top surface. Okay, so at this point here, your pressure is again P plus dp. So you have your dp because you change some height dy at this point here. Now the force due to the pressure on the top surface is equal to your P plus dp times your area A. Now since your pressure exerts perpendicular force, or force at exerted, or force at perpendicular areas. Okay, so here you also have another force. You also have another force here, another force here at this side, and then another force at the back side. But these forces on the four sides of the element just cancel out. Thus, we are left with three forces on your fluid element. So you have a force due to the pressure on the bottom surface, another force due to the pressure at the top surface, and then you have your weight dW. So we have these three forces. And since this fluid element is in equilibrium, or is at rest, the vector sum of the vertical forces in the fluid element must be 0. So the force due to the pressure P on the bottom surface plus the force due to the pressure on the top surface plus your weight of your fluid element, these forces should sum up to 0. That is your PA minus your P plus dPA, because your force here is downwards, minus your dW, the weight of the fluid element. The sum of these three forces should be equal to 0. We're going to use this one to derive some equations later to find for the pressure as your height y varies. And assuming again that the density rho has the same value throughout the fluid as does the acceleration due to gravity, we can find that the pressure in the fluid of uniform density is equal to your P2 minus P1. This is equal to negative rho g times y2 minus your y1. There is a derivation of this formula, basing on the figure and basing on the forces on the previous slide. So there's a derivation of this one, which you can look into the university physics book if you are interested. But the pressure in a fluid of uniform density is equal to your P2 minus P1, which is equal to your negative rho g times y2 minus y1. So you can use this one to find for the pressure anywhere here as you change your height y. It is convenient to express the previous equation in terms of the depth below the surface of the fluid. So this time we are going to look at the surface here at the top, okay? And at height, or at depth h, the pressure P equals the surface pressure P naught plus the pressure rho gh due to the overlying fluid. So you have your P2 minus P1, which is equal to your negative rho g times your y2 minus y1. If we take P2, which is at the surface here, as your P naught, we are now going to take this one as your reference, the top surface here as your reference, and then anywhere around this point here, going downwards at some depth h as your pressure P. So your pressure equation becomes your P naught minus P, which is equal to negative rho g. And here, your y2 is anywhere going downwards. And since your y2 minus your y1 is just equal to the height from the surface here, so we can replace this one with your h. Thus, your pressure equation becomes your P which is equal to P naught plus rho GH. That is, the pressure, P, is equal to the surface pressure, this one, plus the pressure anywhere around here. That is why, as you can see, if you go deeper and deeper to this fluid element or to this fluid, your pressure is greater at lower level because you're adding rho GH to your uh, uh, pressure P naught, or to your surface pressure P naught. The figure here is what we call your Pascal's basis. So your Pascal's basis have different shapes, but as you can see, if you're going to pour some liquid on this basis, you'll see that the water level on each of the bases is at the same height h. So they are at level height, and this is because the pressure at the top of each fluid column is your atmospheric pressure. You have the same atmospheric pressure here, the same pressure here, which is your atmospheric pressure, also the same pressure here, and also the same pressure here. And as illustrated in the figure, the shape of the container does not matter when you're going to look into the pressure at the depth h in a fluid of uniform density, and the fluid or the pressure anywhere around here is just equal to your P is equal to your P naught plus rho GH. Hence, all the columns are the same height. Another interesting principle or law which we can use, or which is very useful when talking about your pressure, is your Pascal's law. So from your pressure formula, which is equal to your P is equal to your P naught plus rho GH, we derive your Pascal's law, which states that the pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and the walls of the containing vessel. Say, for example, you have this figure here. This is common in car shops or in gasoline stations. So you have here a container which is enclosed. Okay, so there's no way that this fluid element will escape of this container. And it is said from your Pascal's law that if you're going to apply a force here, okay, this force will be transferred to anywhere around your, or this force here will be transmitted and diminished to every portion of the fluid and the walls of the containing vessel. Now, since these pistons here, this area here, and then this area here are movable, then if we're going to apply some force here, this force will be transmitted here. That is why what you see here is, if you have a small force that is applied to a small piston, and because the pressure P is the same at all given points at the same height in the fluid, you can apply the small force F on your, or on your area A1 to be able to move a piston of larger area at the same height which experiences a larger force. So applying a small force here will make you be able to move a car, a very heavy car, upwards by just applying the small force. But since as you're going to transfer this force here in the fluid, this force here will now become a lot more greater. So the hydraulic lift shown in, or the hydraulic lift shown in the figure, is an application of your Pascal's law. Question before we end this video. This is about your absolute pressure and then your gauge pressure. The question is, what is the pressure difference between the inside of the car tire and the atmospheric pressure? Again, what is the pressure difference between the inside of the car tire and the atmospheric pressure? A, is the pressure inside the tire is equal to the atmospheric pressure? B, Is the pressure inside the tire is greater than the atmospheric pressure? Or C, is the pressure inside the tire is lesser than the atmospheric pressure? We're going to answer this question in the next video.